Thank you, Caroline, for the introduction. And the subject for the talk for today is supporting the entire life cycle of streaming data. And we'll talk about how Pulsar achieves that. And before starting talking about this, let me first briefly introduce myself. I'm Matteo Merli. I'm the CTO at Streaming Native, and I'm one of the co-creators of Apache Pulsar, and I'm also the PMC chair for the project. And I'm also a PMC member for Apache Bookkeeper. Before talking about the data lifecycle, let me do a quick recap on a topic that we have been discussing a lot in the past, and I just want to expand a bit more to set the context. So we've been talking about data in motion and what messaging and streaming mean. So if you think about messaging is typically message passing between different components, applications, and services. And these different components will exchange messages in order to coordinate between each other and to perform certain operations. Conversely, when you think about streaming, you are doing analytics on events that just happen. In that case, you have a stream of events, and you are applying some processing logic to extract information and record that processing output. If you have to kind of like map these two paradigm to different use cases, typically you will see that messaging is used in online transaction processing and integration between components. These are the main use cases. And messaging has its own set of challenges. Typically, the challenges are around latency. You want to have low latency because there is a user waiting for this message to be published. And you need to have availability and durability because it involves user actions, and you don't want to lose those actions because that would be a bad experience from a user perspective. But also, messaging typically revolves around higher level features in terms of like complex routing of messages across different topics and different consumers, or dead letter queues in which you have like a retry of messages processing and finally routing to other topics, or like topic delay, message delays, individual message delays, or individual acknowledgements. So these are all more complex way that the consumers and producer interact with the system in order to achieve easier coordination on the end. On the other side of the aisle, you have streaming, and the key use case there is real-time analytics. So you want to apply, you have a distributed stream compute framework system, and you are applying this logic on the incoming field of data. Typically, historically, the main challenges of streaming system for storage in particular are around the throughput, sustaining a large throughput because there's a lot of events coming in from multiple different services and servers and so on. So you have like basically a very high fanning of data. And there are also typically challenges around the ordering of the data. That is important, especially in the concept of stateful processing, in which you are kind of like reconstructing a state, and you have to basically process the events in a certain order. At the same time, you want to be scaling up into multiple nodes. So that's kind of like where the challenge stems from. And finally, you typically have challenges around handling in a good way the batch processing and the real-time processing, because they are accessing different portion of the data, the hot data versus the cold data in batch jobs. And you might have these happening together on the same system. So the system has to be able to support equally well these two kind of access pattern. But the question now is that, okay, we talked about that Pulsar is well suited for this, but why and how? So how Pulsar can support both of these usages. And the main reasons are two, and the revolves around the scalable log storage, in which we can scale the data ingestion and the data reading in a very efficient way, because the immutable log is the best way to store this kind of data for this access pattern. And but also the log is not enough for everyone. If you have more complex interaction with the system, you need a more flexible messaging semantic. You have this more complex interaction between system, and therefore the API has to be more high level. So we kind of built that on top of this scalable foundation. And these are not the only two reasons why Pulsar can support both messaging and streaming, but are the most core one. The next question is, okay, Pulsar support messaging and streaming, and but why it is important? Why it is relevant? Or why cannot I use one messaging system and one streaming system for to solve these kind of problems? And there are a few reasons, and if you look at it from a high-level perspective, you can see that often the messaging and streaming processing and ingestion of data is applying the processing in different stages of data, but they're handling the same data. So you might apply the same processing on the online world, but then apply that kind of like different processing on the same data in the analytics world. So that's kind of like one of the things that you see and say, okay, this should be combining into one. That's one hint here. The other part is that when you're integrating different systems, you have a lot of like impedance mismatch, and you might have multiple components on one side, multiple components on the other side, and the resulting system is often very complex. You don't know where the data is coming from, where it's going, and who is talking with who, and it's a very complex architecture, and it becomes very fragile because you don't know which component is going to break, and when it breaks, what is gonna cause breaking all the components too. And finally, it can be fairly inefficient in the sense that you might have to either wait for the other system to be up, or like write data twice in both system, and you have the data duplication with higher cost and so on. So when we're talking about messaging and streaming, then we can map this into kind of these two islands, right? So you have the online side and the offline side. And on the online processing, we have messaging, and on the offline data services, we have the streaming, in which we are taking the feed of what happened, new events that are happening from the online processing world, and we're gonna do analytics on top of it. And we can see how Pulsar can kind of bridge the two worlds together. If you're taking that individually, right, this is a very simple example, not trying to make a complex real-world example. I'm just trying to make a simple point here. So you might have microservices, an application composed of microservices. These microservices will accept HTTP requests. And one such request for service A could be new user sign up. So you have to create a user in the system. And you might want to do this in an asynchronous way, because you might have another service that is handling some pre-checks that you want to do when the user is created, and has some processing logic, and then finally it will write into the database. But between these two services, since you want to do it in an asynchronous fashion, you have a messaging service in form of a topic. So service A gets a request, it would publish a message on the topic. When its message is published, then service A is free to move on, and service B will take the message, will do something, and write it on the database. And finally, the service A might be reading from the same database and get the updated resulting state after it. On the other side, we have streaming analytics, which, as we said, it works in the form of, you have a messaging service from which you have an unbounded stream of events that already happened. and the stream processing framework will read those events, apply the processing logic, and then will write some result. And that result could be writing into an analytic database, or could be writing into some other system where you're writing your output of the computation. The computation could be the analytics. You can do some very, very complex analytics there, or it could be some, for example, like some machine learning updated model that was updated with the new data based on the new data. And what is typical scenario of interaction here between the online and offline is not just the stream of events that move from online to the streaming analytics, but is the realization that in almost all the cases, you have to basically be able to feedback the updates into the online side. And that is because when you're applying streaming analytics, you want to make the decision very quickly. That's why you have this sub-second latency in the processing. You want to process the data as fast as it comes in to have a very little gap there. But when you're making some decision, updating some of the state, you want to be able to get that state back and tell the online services that something that they have to change something in the configuration, for example. Or one simple example here could be the fraud detection use case, in which you have a stream of events, and in your processing analytics, you might detect that there is a pattern of fraud that is happening in the system. A particular user might be trying to do something that is suspect. So you want to apply some countermeasures. You want to disable this user, disable the IPs that is request coming from. So you want to basically use the full loop here to have the state of the result of the analytics feedback into the online state as quickly as possible. And this is not just a technological problem. There are technical challenges, yes, but there is also a component that is more like an organizational problem, in the sense that you have these online services that streaming analytics traditionally are handled by different teams, different organizations. So the talking between each other gets more complex because of that. And the interaction are complex because you have a lot of questions. These are like a very open questions. Can be who's responsible for getting a feed of events into the streaming analytics? Is like a pull model, push model? Who's going to do that? Which side? Or where is the data going to be stored? Is it going to be stored in a database in the online side, and then it gets pulled out, or it gets stored into a messaging system into the streaming analytics side, or it gets stored in both, and what is the source of truth, and so on. And then you have questions about how can we circle back and update the online data store, which are typically not accessible, not writable from the compute framework directly. Or what happens regarding availability when one of the system, who is talking to who, and when one system is down, what is going to happen? Is the data path going to be impacted or not? And down to questions like how the schema of data is enforced. Each system might have its own schema, operational part, but when you're crossing system boundaries, that will not get enforced. And finally, what is the security model here? So the question is, what if we just put everything into a single data platform, both microservices and streaming data pipelines? We can run that into a single Pulsar instance, and at least some of our problems will be solved, right? And if you expand a bit this view, we can have the same microservice analytics. We can expand from the first case, and now we have a service A and service B that communicate across with the topic, but you also have a stream processing job that is reading from the same topic. So it is reading the same data, the same exact data for a different purpose, and it is doing its own computation, and then it is sending the results of this computation into a different topic. And now you might have a service C that is getting the output of this outcome of the processing job, and it is able to write that directly into the service database, for which service A will get the updates very immediately, essentially. So essentially, like using the topics as a way to communicate between services on different sides, we can have like a very clear point of integrations and so on. So if you look at these integration points, the idea here is that you have all these kind of services that are all sharing the same Pulsar cluster, and you want to decouple services through topics. And the reason you do that is that you want to provide isolation between these services, and you want to have guarantees on the availability. So if you're going through, if each service to another through a topic means that the availability of the topic is guaranteed by the availability of Pulsar, but the individual services might go up and down. The stream processing job can be down for a certain amount of time, and nothing will impact the operations on the system as a whole. So if you're using Pulsar as a single data platform, what you get essentially is have a single tooling, a single system, but a single system that can support multiple APIs. And we'll show a bit later what these APIs are. But you also get a unified authentication and authorization for access to the data. So you can have defined rules across the board on who can publish the data on these topics, who can consume it, and you can enable like all this kind of access as needed. And you also have end-to-end schema validation, because this can get carried over from topic to topic. So eventually, all the data you can have all the lineage of the data and the schema evolutions across all the system. And I want to spend a word here about data ownership. I want to qualify also a bit more. So if you're thinking about data that resides in silos, you have the online system that has its own messaging platform and that owns its own data. That's kind of like if you want, is an anti-pattern. You don't want to have like one component to own the data. The data is not owned by one single component. You have different components that are interacting between each other by sharing data. So no one owns that data. And you want to keep one copy of the data so that is the single source of truth of the data. And you want to be able that consumer components can get direct access to the data from the source. And that means that at this point, you have no need for ad hoc integration. So each component talks with each other through a topic, and that is the well clearly defined way to interact. There is a schema, there is availability guarantees, and that's kind of like a well clean point of integration. And then once you look at this from a high-level perspective here, you can see that the data throughout this exercise of these different components that are generating data, processing data, and outputting the processing of the result of the data processing into the same Pulsar cluster, you can see that Pulsar, it is managing the entire life cycle of data. So the data, since it is inception, throughout all its transformations and all aggregations or analytics and all the results of these analytics, and down to the long-term storage of the data. And you can qualify here the different stages of the data lifecycle. So you have events that are happening, the microservices interacting between each other. So that's more like a real-time happening of events. And then you have streaming analytics, which is generally is like you try to target like sub-second processing of the data. In some cases, it can be like less than 100 milliseconds, but that's kind of like the ballpark for it. And you can also have data replays. For example, like if you want to roll back streaming analytic jobs to few hours or days, so that they can reprocess the data again. and down to the long-term storage of data, so that you can apply batch processing jobs on this data, and there the data retention can be measured in terms of days and even months in the system, and all this in the form of a stream of data. So you can always go back and replay your entire stream, even if it's month worth of data. So the key point of managing here the data lifecycle are that, one, we want to store the data only once. We want to make it available to everyone that is interested, and we want to be able, we need to be able to hold the data for extended amount of time. So the system has to guarantee like all these properties. And Pulsar provides an infinite stream storage abstraction. So when you're looking at a stream of abstraction, you want to have large throughput, yes, for granted, but you also want to have like low latency writes that are very important for online writers, for example, and also you want to have isolation between tail read and catch-up reads, because that's kind of a different access pattern that can, and you don't want this impact each one of them to impact each other. And the long-term tier storage, so that can offload the older data to a cheaper storage like S3 or GCS to have an unbounded amount of storage capacity at a low cost. And another key aspect to achieve this overall data platform is that the system needs to be able to isolate different workloads. Since we are like running multiple workloads, one of the important aspects here is that Pulsar, it is designed for multi-tenancy and multi-workloads since the beginning, and all these come from like having I/O isolation at every level, but also having like limits that are automatically applied around throttling quotas, or that you can apply explicitly setting resources limitation on certain namespaces or use cases of topics, and you can prioritize different kind of use cases versus each other. In that case, you can achieve basically have guaranteed set of resources for certain use cases and have like best effort for others, for example. And once we put everything together, like we do have a single system, a single platform that can support very well microservices using different messaging protocol, either the native Pulsar API or things like MQTT protocol, MQP, or Kafka protocol. They are all supported natively by Pulsar protocol handlers. At the same time, we also have streaming and batch data pipelines that are supported through a more low-level storage, like kind of a reader and batch API. And all this gets integrated with the tier storage that offers this infinite stream storage for the data for long retention. And finally, there is things like Pulsar IO connectors that are used to have predefined sources and sinks for data, so that data can be easily integrated with different systems without writing code, and also with Pulsar functions, with which you can is on the way that you can apply this processing logic. And concluding here, I hope that I made the case that clearly that Pulsar, it is uniquely suited to be the data platform that powers all the data in motion use cases and all the interaction because of its design and because of the unique set of features and unique set of this decision that makes it possible to have this kind of interaction in a safe way, in a very clear and in a clear, effective, and efficient way. So thank you very much, everyone, and have a good Pulsar Summit.